Hey guys, Miss Marisic here, and in this video we're going to talk about solving problems dealing with the ideal gas law, either in its original form, in its substituted forms, or even in the rearranged form where we end up having the combined gas law. So to start us off here, we're given a problem that asks how many moles of oxygen gas must be put in a 500 milliliter flask at 20 degrees Celsius to have a pressure in the flask of 850 torr. And the first thing I do whenever I see one of these problems is I go and identify my variables, both the variables that I know and the variable I'm trying to solve for. I can see here I'm trying to solve for how many moles of oxygen gas. So I'm trying to solve for N. 500 milliliters would be a volume, 20 degrees Celsius would be a temperature, and then 850 torr would be a pressure. So I can see I'm presented with one set of conditions for moles, volume, temperature, and pressure. And so when I have one set of conditions, and that probably means I'm doing a variant of PV equals nRT. Now, the one variable I do not have yet is R. So I need to go and select a value for R based off of my pressure unit. Since my pressure unit was in torrs, I'm probably going to want to use this 62.36 in order to get all of my units to cancel out. I wouldn't want to use the one with ATM or this one that had kilopascals because those wouldn't match up with the pressure and allow the units to cancel. So I'm going to come over here and go ahead and write that I'm going to use PV equals nRT. And I'm also going to write my R variable that we decided to use, 62.36 liters times torr over moles times Kelvin. Now here's the deal. I need to make sure that all of my other variables besides the pressure match up with this unit as well. If they don't, then what will happen is my units won't cancel out appropriately. So looking here, I notice that this unit has liters in it. Well, right now my volume is in milliliters. So I'm going to convert that really quick. I know milli is 10 to the negative third, so I need to move that decimal over 3 places to get into liters. And since liters are bigger than milliliters, I should have less liters. So I'm going to have 0.5 liters once I move that decimal over 3 places. Now for temperature, I need all temperatures to always be in Kelvin whenever I do a gas law problem. Now conveniently on my formula chart here, I have that Kelvin equals degrees Celsius plus 273. So if I add 273 to 20, that will get me to 293 Kelvin. And then of course we already made sure that the pressure matched up and moles would match up with what I'm trying to solve. So now I'm ready to plug in everything into my equation. So again, my pressure is going to be 850 torr. My volume is 0.5 liters. My N is what I'm solving for, so if it makes you feel better about solving algebra, you could always put X there. My R is 62.36 liters times torr over moles times Kelvin. And then my temperature was 293 Kelvin. Now, I went ahead and wrote the units here so I could talk about how they cancel. When I have a unit on top on both sides of the equation, then those would cancel, so torrs and liters would both cancel. And then if I have a unit both on top and bottom on the same side of the equation, those would cancel as well. So Kelvin and Kelvin would cancel. Now when I'm left with divided by moles here, what that means is that this N must be moles, so that way moles divided by moles would eventually cancel, which is good because that's what I was trying to solve for. So now I'm ready to go ahead and plug all this into my calculator. Now to do this, I want to solve for N. So again, think of that as your unknown variable X. And so to get that by itself, I would want to divide these other two numbers over to the other side. So that would leave me with 850 times 0.5. Then I'm going to divide over the 62.36. And I'm also going to divide over the 293. And that gets this lovely number right here. Now, obviously, I don't want to have to report all those digits, and so I'm going to think about what I would need to do to round for sig figs. If I notice, all my original numbers have 3 significant figures. So to round this for 3 significant figures, I would report that the number of moles is 0.0233. And again, we said that that would have a unit of moles. All right, let's try another one. The next one asks, hey, what is the molar mass of a diatomic gas if 1.60 grams of it in a 500 milliliter container exerts a pressure of 2,500 millimeters of mercury at 350 Kelvin? And I'll also ask, what is the identity of the diatomic gas? So we'll deal with that here in a little bit. So to start us off here, I'm going to identify all of my variables. I'm looking for molar mass, which as a reminder is that bolded italicized M. 1.60 grams is a mass, 500 milliliters is a volume, 2,500 millimeters of mercury is a pressure, and then 350 Kelvin would be a temperature. So yet again, I see one set of conditions of everything, and so I know I'm going to be using some variant of Pivner. However, here I don't have moles, I have mass and molar mass mentioned. So it might be really helpful for us to do this substitution in that N, the number of moles, equals mass divided by molar mass. So don't forget, the bolded italicized M is molar mass, it tells us that over here, versus down here where we have molarity, you see that one is not bolded, so just be careful. This is molar mass here that we're dealing with. So I'm going to go ahead and write that substituted equation, PV equals mass over molar mass, RT. And I can see that, oh, I'm probably going to have to pick an R value. Now here we have 2,500 millimeters of mercury for our pressure. And if I go look at my R values, upon first glance, I'm like, well, wait a minute. This would have had kilopascals in it. This has atmospheres. This has torr. It doesn't look like there is one for millimeters of mercury. However, if I look here at my pressure equalities, I notice that the millimeters of mercury scale is exactly the same as the torr scale. So even though this 62.36 has torrs in it, I can actually also use it for millimeters of mercury as well. So I'm going to write that I'm going to use the R value of 62.36 liters times millimeters of mercury over moles times Kelvin. And again, before I plug in, I need to make sure all of my units match up. Now, molar mass is going to be a grams per mole situation because I have the grams for the mass right here. So that's where those units will match up. But this milliliters needs to be in liters. So just like we did a minute ago, this will become 0.5 liters. Our millimeters of mercury obviously matches up because we selected that. And conveniently here, our temperature is already in Kelvin. So that means I'm ready to plug everything in. So my pressure was 2,500 millimeters of mercury. My volume, we made 0.5 liters. The mass is 1.60 grams over the molar mass, which is our X, our unknown variable here. My R, 62.36 liters times millimeters of mercury over moles times Kelvin. And finally, my 350 Kelvin. Now again, I did go ahead and write the units here because I want to talk about how they cancel. Millimeters of mercury on top and top cancel. Liters and liters on top both cancel. Here, the Kelvin on top and bottom cancel. And if you notice, that leaves me with grams divided by moles, which makes sense if I'm trying to solve a molar mass. Now here, it's kind of awkward because that molar mass is in the denominator, in the bottom. So when you're trying to solve an unknown variable in the bottom, remember, one of your first steps needs to be to get it out of the denominator. So what I would do is actually multiply both sides by that molar mass to bring it to the top, to bring it into the numerator. So now I can see to get it by itself, I would want to divide both of these two numbers over to the other side. So that would leave us math-wise with 1.60 times the 62.36 times the 350, and then I'm going to divide over the 2500, and I'm also going to divide over the 0.5. And when I do all that, I end up with using 3 sig figs. Again, I noticed most everything had 3 sig figs up on the top. So I'm going to report a molar mass of 27.9 grams per mole. Now, in thinking about a diatomic, if this represents 2 elements together, if I divide that by 2, that gets me roughly about 14 apiece. And if I go look at the periodic table to go find an element that's about 14 grams per mole, I will find that that is nitrogen. So that means this diatomic molecule must be N2. Now, does the molar mass come out perfect? No, it doesn't. But again, it's experimental data, so it may not be on the nose perfect. All right, let's look at another one here. It says on this one, a gas is stored in a rigid container at 800 torr. And I'm like, ooh, rigid container, that might mean that my volume is constant. If the pressure of the gas is decreased by 300 torr, and at the new lower pressure, the temperature is found to be 40 degrees Celsius, what would have been the original temperature of the gas in Celsius? Now, something I'm kind of picking up on here. First off, they mention that, hey, I have an initial pressure, okay? And then the pressure of the gas is decreased by 300 torr. So that means I have a new pressure of technically 500 torr when I decrease 800 by 300. And then it says at the new lower pressure, we have this temperature here, and it wants to know what was the original temperature, meaning I have 2 pressures mentioned, and I have 2 temperatures mentioned. I have changing conditions here. Now, when I have changing conditions, what that means is that I'm going to be using some sort of variant where I have the combined gas law, where I have P1 times V1 over N1 times T1 equals P2 V2 over N2 T2. Now, I notice that only pressures and temperatures are mentioned as changing. They don't mention amount at all, so I assume that stays constant. And they told me I had a rigid container, so I would assume that volume also stays constant. And so I can see here I'm essentially using the equation P1 over T1 equals P2 over T2. I'm using Gay-Lussac's law. Now, I have to be careful for my units here. First off, I need units to match. And so I see I have 800 torr and 500 torr, so that matches. But the temperature, while they might match, they're not in a good unit. Remember, for these to work out, your temperature must be in Kelvin. Even though it wants the original temperature in Celsius, that doesn't matter. I still have to calculate this in Kelvin or it doesn't work out. So my 273 plus the 40, that would get us for that a temperature 313. But I got to be really careful what conditions I'm putting together here. It says that at the new lower pressure, the temperature is this 313 Kelvin. So what that means is that this temperature and this pressure need to go together. So I'm going to set those as my second set of conditions, and I'm going to be solving the initial temperature for the initial pressure. So now that I kind of have that all labeled, designated out, my units converted to Kelvin like I need them to be, now I can go ahead and plug in. So my 800 torr as my P1 over my T1, which is what I'm looking for. So if it made you feel better, you could always put X there to solve. I'm going to have that equal my P2, my 500 torr, over my T2 of 313 Kelvin. Now, on these, I typically use cross multiplying. I know that these two multiplied will equal these two multiplied. And so when I do that, I would have 800 times 313 equals 500 times T1. And so then these two multiplied, I would divide by 500 to get T1 by its length sum. So there's lots of different ways to do this algebra. And honestly, if you're doing it in a way that makes sense to you, where you're getting the correct answer, that's totally cool. But again, I would do 800 times 313, so cross multiply those, and then I would divide by my 500. And I see that gets a T1 of 500.8. Now I have to be careful here because right now that is still in Kelvin. And if I look back at my question, it wants us to solve the original temperature in Celsius. So to convert Kelvin back to Celsius, I would end up subtracting the 273, which gets us to 27.8. Now, I'm going to go ahead and round for sig figs. I notice everything in the original problem had 3 sig figs. So I'm going to round this to 228 degrees Celsius for my temperature. Okay, let's do one more together here. On this last one here, it says, hey, a gas is known to have a volume of 7.81 liters when the pressure is 754 torr. What would be the volume in liters when the pressure is changed to 1.23 atmospheres? Now, I notice again that I have 2 times that volume's mentioned. I have 2 times that pressure's mentioned, so I'm probably going to be doing another variant of our combined gas law. Let's see exactly which variables I need. I notice I have a volume here, I have a pressure, then it's asking me about a new volume at my new pressure, and so I'm not going to need the number of moles. I assume that to stay consistent. And I'm also not going to need the temperature. If they don't mention something, we can assume that it remained consistent. So I'm going to be using the equation of P1 times V1 equals P2 times V2. And you notice these are multiplied and not divided because they are an inverse relationship. As the pressure increases, the volume would decrease and vice versa. Okay, now I do need to check my units. Now, something nice about the combined is that it doesn't matter what unit either of these are in as long as they are consistent in the problem. So for volume, as long as both of my volumes were in the same unit, it really wouldn't matter what unit they were in. I notice here they are both in liters, and so hey, that works out great. But even if they were both in milliliters or they were both in centimeters cubed or meters cubed, as long as they were the same, you wouldn't have to do any kind of conversion with them. However, I notice my pressures are not in the same unit. Now, this is where you get to choose. You could either leave them both in atmospheres or you could leave them both in torrs. You get to kind of pick as long as you convert one into the other. So I'm going to go ahead and convert the 1.23 atmospheres into torrs. And to do that, what I need to do is I need to use my pressure equalities that are on our formula chart. I notice that 1 atm is equal to 760 torr. So if I do a quick dimensional analysis where I say, hey, 1 atm is 760 torr, I can figure out what that pressure value should be. 1.23 times my 760, and that comes out to 934.8. Now, since I'm not done with the problem yet, I'm going to resist the urge right now to round for sig figs. I'm just going to go ahead and use the 934.8 torr. Now, I do need to figure out kind of which variables need to go together. The 7.81 liters, that needs to go with the pressure being 754 torr. So I'm going to set those as V1 and P1. And then I'm going to set this new volume as V2. Now this P2 is actually going to be this value down here versus the 1.23 atmospheres since we converted it. So now that I've got everything kind of matched up, I've got everything in the same unit, now I can go ahead and plug these into my calculation. So my P1 is 754 torr. My V1 is 7.81 liters. My V2 is what I'm looking for. My P2, 934.8 torr. So again, if it makes you feel better, instead of putting V2, you could always put X there as what you're trying to solve for. So to get V2 by itself, I'm going to divide the 934.8 torr over since those are multiplied. So that's going to be 754 times 7.81 divided by the 934.8. And when I get this lovely answer here, I'm going to go ahead and round for 3 sig figs because all of my original numbers have 3 sig figs. And so I'm going to round this V2 to 6.30 liters for what I'm solving for. All right, hopefully we're kind of remembering how these gas law calculations work. Hopefully it's kind of coming back to us. Just be very, very careful on what you're labeling and making sure your units match up. Make sure that we're either matching our units up to R or matching the units up to each other. And always make sure our temperatures are in Kelvin. That's probably the biggest mistake I see people make, especially when you have a problem like this where it wants the final answer in Celsius. So just be really careful on that. All right, hopefully we're feeling good. If you have any questions or need any help, please feel free to email me. Bye, guys.